Today we're going to take a look at Taylor series. This is kind of a continuation of Taylor polynomials, except instead of stopping at some particular degree, we continue on to infinity. A quick review of what we've done so far with Taylor polynomials. First off, the Taylor polynomial is in general the best polynomial approximation to some function that is differentiable n times. In other words, you can take its derivative at least up to the nth derivative. The process of finding a Taylor polynomial began with our list of requirements, and that list was that the function that we're trying to approximate and the polynomial had to have the same value at 0. They had to have the same slope at 0, the same concavity at 0, and so on, until we just decided that the original function and its Taylor polynomial should have the same derivatives at 0 up to whatever degree we are interested in. Now, in general, we can center a Taylor polynomial around any point x equals a, but it's often convenient to use the point x equals 0, so that's where we have focused our attention so far. With 0 as our point, the formula for the Taylor polynomial is given here. Our job in finding an unfamiliar Taylor polynomial is to just plug in all of these derivatives evaluated at 0. All the rest of the formula just remains as is. So we set about taking our function, we plug in 0 to get the first coefficient, we take the derivative and plug in 0 to get the second coefficient, and so on. We did a few examples. One is the sine function. So we found that its Taylor polynomial consists of only odd-powered terms, and the signs of those terms alternate. One of the problems in the last worksheet was to write down a formula for the nth term of the Taylor polynomial. So that would be here for the sine x. And just to think about this a little bit, if we were to plug in any value for n, notice that the exponent stays odd. So if n were 0, we would get x to the first. If n were 1, we'd get x to the 2 plus 1, or x cubed. If n were 2, we get x to the fifth, and so on. Similarly, the factorial in the denominator matches that. So at n equals 0, we get 1 factorial, or 1. For n equals 1, we get 3 factorial, and so on. Finally, the minus 1 to the n is what controls the sign of the terms. So if n is 0, minus 1 to the 0 is just 1. And that's good because we start with a positive term here in the x. Minus 1 to the first is minus 1. So that gets us the correct sign here for the x cubed term, and then it just alternates back and forth. A second example that we've done is the Taylor polynomial for e to the x. Once again, we have the formula for the nth term is reported here. So that allows us to know how to go out to a Taylor polynomial of any degree. We just know that whatever the degree is, say degree 105, the last term there would be x to the 105 divided by 105 factorial. Now, we made note of the fact, both graphically with the GeoGebra applet and in our calculation examples, that the more terms we take in our Taylor polynomial, in general, the better we do at approximating the function. This leads us to the idea of Taylor series, which we can just think of as infinite Taylor polynomials. So the idea here is that if a Taylor polynomial gets closer and closer to our function as we take more and more terms, or higher and higher degree, then if we take infinitely many terms, we'll get an exact value for our function. In fact, we'll get an alternate way of writing down some of the familiar functions we see. When we take a Taylor polynomial and don't stop, we get an infinite series representation of the function called the Taylor series. We can turn a couple of our examples from class into Taylor series fairly easily. For the sine of x, we have only odd powers, alternating signs. We know how to write down the nth term. So this infinite sum expression would be the Taylor series for sine x. Starts at 0 and doesn't end. Similarly, since we know the Taylor polynomial for e to the x and we know how to write down its nth term, which is here, we can write down the Taylor series expansion for e to the x. Now, an important difference between a Taylor polynomial and a Taylor series is the fact that we don't have the wavy equal signs representing approximation. We have actual equal signs, right? These are exact values now. They are not approximations to our functions. They are alternate ways of writing down the function. A bit of math trivia for you here. You may remember that the sine of x is an example of what we call an odd function. And similarly, the cosine of x is an example of a function that we would call even. That language actually comes from Taylor polynomials and Taylor series. So any function that has only odd values in its Taylor series expansion, we call an odd function. Any function that has only even powers in its Taylor series, like the cosine does, is called an even function. So that's the reason for that language. And then if we think of them graphically, an even function is symmetric across the y-axis, and an odd function is symmetric around the origin. Now, as soon as we write down an infinite series, all of the work we did in the last chapter comes into play, because we have to know where infinite series converge and whether or not they converge. So anytime we are taking an infinite sum, summing an infinite number of terms, we have to be a little bit careful about whether that sum is going to converge or not. And if it is, we need to know where. So in general, we call the set of values where a Taylor series does converge the interval of convergence. We have 3 possibilities for the interval of convergence, and only 3. First off, sometimes a Taylor series will only converge at a single point. When that's the case, it's going to converge only at the point that the series is centered around. So for us, x equals 0, but in the general case, it could be x equals a. Secondly, the series could converge on an actual interval around x equals 0. So in that case, the series would converge on some interval, say minus r to r. And then one thing that we probably won't deal with very much is that we actually could have all 4 different possibilities for convergence based on whether the series converges at the endpoints of the interval. So all 4 of these intervals that I'm writing down could be an interval of convergence. They're all symmetric around 0, except perhaps at the endpoints. We might have convergence at minus r, say here, but not convergence at r. We might have convergence at both minus r and r, or neither minus r and r. But these are all examples of intervals of convergence. And again, if the point is x equals 0, then that is going to be a symmetric interval around 0, except perhaps at the endpoints. Our final possibility for the convergence of a Taylor series is it might actually converge everywhere. This is the best possible case for us. And we can write that as an interval minus infinity to infinity, or it's also just fine to say that the series converges for all real numbers. We'll see in our examples different types of intervals for convergence and how to find them. Our first example is to find the Taylor series for the function 1 over 1 minus x near x equals 0, and also to determine the values of x for which the series converges. Well, from our last worksheet, we know that the Taylor polynomial for this function looks like 1 plus x squared. And the nth term for this one would just be x to the n. So our Taylor series is the infinite version of this Taylor polynomial. So it's going to go from n equals 0 to infinity. And it's just the sum of terms that look like x to the n. So we found the Taylor series. Right? If we hadn't done the work to find the Taylor polynomial already, we would have had to start finding derivatives, plugging in 0, using the formula, and so on, and then getting to the series. But since we already did that work, finding the Taylor series is really just a matter of using the infinite sum notation. The next question is, where does this series converge? Well, to figure that out, we go back to the ratio test. So let's see how that's going to look. All right, so we take the limit of the n plus first term divided by the nth term, remembering to keep the absolute values. I can cancel x to the n plus 1 over x to the n and just get x. That means I no longer have an n in my limit. So as far as n is concerned, this is a constant, and the limit will just be absolute value x. Now this ratio test, remember, gives convergence whenever the resulting limit is less than 1. So in this case, we have convergence for x less than 1. That means x is between 1 and minus 1. And that means the interval of convergence is the interval from minus 1 to 1. Notice it's symmetric around 0. And for us, we're going to stop there. We're not going to test the endpoints separately. So our interval will just be the open interval from minus 1 to 1. In the example we just did, the ratio test told us that we should only expect convergence for the Taylor series near x equals 0 for the function 1 over 1 minus x between the points x equals minus 1 and 1. Now we've actually seen this in action from the previous worksheet if you got to the GeoGebra applet question. Here I've opened up that applet again, and it's the one that plots Taylor polynomials for us. And what we're going to do is take a look at how the Taylor polynomials behave as we increase the degree, as we add more and more terms. So here's the best straight line approximation, n equals 1. Here's n equals 2, so the x squared, x cubed, and so on. Here I'm at n equals 6, and I'm just going to drag the slider so we quickly get a bunch of Taylor polynomials. Notice how we are never getting past x equals negative 1 for our approximation. We're just flipping up and down. We're doing a better and better job, closer to minus 1, but we can't get past it. I'm going to move our window a little bit and show that we're getting something similar happening on the right. So let me start over. All right, so I'm going to drag up, representing adding more and more terms. And we do a better and better job getting closer to x equals 1, but we never get past x equals 1. So this is a graphical demonstration of the limitations for this particular Taylor series. The reason we have that limitation is we have a vertical asymptote at x equals 1, and that prevents the Taylor series from crossing over to approximate numbers like 2, 3, and so on. And because Taylor series converge in symmetric intervals, since we can't get past 1 on the right, we also can't get past minus 1 on the left. Let's do a second example. Here we're going to find the Taylor series for the function e to the x near x equals 0, and also determine the values of x for which it converges. We've already done the first part. The function e to the x has Taylor series representation n equals 0 to infinity, with nth term x to the n over n factorial. So that's our Taylor series. Now if we hadn't done that one, if we hadn't done the work for the Taylor polynomial first, then we would have to start from scratch with plugging in f of 0, finding f prime of x and plugging in 0, finding f double prime of x and plugging in 0, and so on to get all the coefficients, then recognize the pattern, then write down the series. So here we have the series. The ratio test is how we determine where the series converges. That involves taking the limit as n goes to infinity of the n plus first. We'll see in this example and also in examples for functions like sine and cosine that the factorial kind of arises naturally in Taylor series. So the fact that we've been dealing with the factorial in our infinite series material wasn't an accident. And also not just done out of spite, right? It's actually something that we need now to figure out where our Taylor series are going to converge. So far I've instead of dividing by the fraction, I've multiplied by its reciprocal. Next I'll do the canceling that we need. On top, I just have an absolute value of x, which I can pull out, leaving me with a limit 1 over n plus 1. As n goes to infinity, that goes to 0. So the whole limit goes to 0. Now the ratio test says that whenever my limit is less than 1, I get convergence. Well, 0 is less than 1, and we had that for all values of x. So we have convergence for all x. We can write that as our infinite interval of convergence minus infinity to infinity. And generally that's good news. That means that our Taylor series should equal the function e to the x for all values of x. We don't have the limitation we had with the example from before. Let's take a look at this one graphically. All right, we start with the best constant approximation to e to the x. We have the best linear approximation, best quadratic, cubic, and as we go along, we have the sort of flipping up and down behavior that we had before, but notice we're doing better and better as we move off to the left. Now the exponential grows too fast to really get a great picture for a large value of x, but here we can at least see that there is no apparent limitation on how well we can approximate e to the x or how far out we can do it. So for the range that we're showing here, minus 8 to 8, well, we don't see the whole thing, but for what we do see, the whole graph is covered so that it's indistinguishable from the Taylor polynomial that in this case has degree 40. So one thing we need to get in the habit of doing is when we are asked to find a Taylor series, we should first think about whether we already know a series that's going to help. Using the formula for a Taylor series, that would involve first finding the Taylor polynomials. So we would have to go find a bunch of derivatives and plug in 0 and then plug all those coefficients into the formula. And that takes a long time, right? We have to be able to do it for the test for simple examples, but those can get messy in a hurry. So if we do find ourselves trying to find a Taylor series from scratch by finding derivatives, and we're getting a lot of really messy calculations, that's generally an indication that we should try a different way. The main alternate way is to find a series that you already know and try to use that instead. Let's see how we could attack something like f of x equals e to the x squared. Now this one would be difficult to do if we had to find derivatives. So for example, the first derivative would be e to the x squared times by the chain rule, a 2x. The second derivative, we would need to use the product rule. We get derivative of the first times the second plus the first times the derivative of the second, which again requires the chain rule. So this would end up being 2e to the x squared plus 4x squared e to the x squared. So we can see that the derivatives are getting complicated pretty fast. If I took 3 or 4 more, it would start taking a long time to do. So this is not the way we want to approach this one. Instead, let's recall that we already know how to do e to the x. Well, if this is how we write e to the x, then we can find e to the x squared just by plugging the new x in. In other words, instead of x, I've got x squared. Instead of x squared, I would have x squared all squared. Instead of x cubed, I've got x squared cubed. And I can simplify that. So I see I'm getting only even powers of x. And I could also write down the series representation. So here is the Taylor series for e to the x squared. And I didn't have to find any derivatives. The same thing is going to happen with our next example. This one's a little trickier to see. And the derivatives here really wouldn't be that bad, so we could do it the long way. But it's nice to see how to manipulate a known series. I already have done the work for 1 over 1 minus x, or rather you did in class, so that's 1 plus x. And then I can think of 1 over 1 plus x as 1 over 1 minus negative x. So that minus x gets plugged into the series above. I can simplify that a little bit. So I can write 1 over 1 plus x is equal to the sum n equals 0 to infinity of minus x to the n. We could also write this as minus 1 to the n times x to the n. It doesn't really matter which. Now we do have to be a little careful here. In the previous example, since the Taylor series for e to the x is valid for all x, so was the Taylor series we found for e to the x squared. Here, remember that the series is only valid, it only converges when the thing we plug in this case negative x, is less than 1. Absolute value of negative x is the same as absolute value x, and so we have the same interval of convergence, minus 1 to 1, as we did for the original series that we used to get this one. Now that we've done 1 over 1 plus x, we can actually do one that at first looks kind of unrelated, and that's the series for the natural log of 1 plus x. So here's another example of how, if we're clever about it, we can save ourselves a lot of work. The idea is that the natural log of 1 plus x is the integral of 1 over 1 plus x. And we've already done the work to figure out that the series for 1 over 1 plus x is the alternating series of powers of x. That's going to give me x minus x squared over 2 as I integrate each term, x cubed over 3 minus x to the 4th over 4, and so on. Now for an indefinite integral, I still have a plus c to think about. The c is going to be 0 though, because if I plug in x equals 0, on the left I would get natural log of 1, and on the right I get c. That's plugging in x equals 0, but the natural log of 1 is 0. So this c turns out just to be 0, so I can forget about that. So the final version here is natural log of 1 plus x. We can write as the infinite series. N equals 1. We need to alternate the sign, but start it at a positive number. So I'm going to have minus 1 to the n plus 1, x to the n over n. And this is only valid where the last series was, for absolute value of x less than 1. So minus 1 to 1. All right, so we've seen how to define a Taylor series just as an infinite Taylor polynomial. We have gotten a little bit of practice in writing down the nth term of a Taylor polynomial or Taylor series using a formula. And we've shown how, at least a couple of examples of how we can use old series to get new ones almost right away, certainly without all the work of finding the Taylor polynomials first. On the worksheet, we'll have some more examples of finding Taylor series in this way, and we'll also see some of the many different ways that Taylor series are useful. I'll see you in class.